So let's say you have a grid, and this inverse transform or any sort of transform, sampling transform, will transform it into a grid which is stretched. It's usually not stretched like this, like uniformly, because this is a rectilinear. So it's a rectilinear stretch. So the two axes are stretched independently completely, but sometimes it's like like a kitchen foil stretch. So certain parts can be stretched more than others and be very localized. But with regards to random sampling, if you're not seeing the connection straight away of why the changing of areas will make samples generated uniformly transform into samples which are generated according to the PDF, we need to talk about the duality of basically probability and sampling. Because if you're thinking about a grid and discrete samples, then you might not be confident why that would work. But if you're talking about an infinite amount of samples which cover the domain completely, because there's an infinite amount of them, and you're talking about a continuous function which remaps some of the samples into new, remaps the samples into new positions. And because there's infinitely many of them and they're infinitely closely together, between any two samples, there's always another sample if you have infinitely many, that are well distributed, then you can see that intuitively this should work. But to get down to it more formally, we could think about area as some sort of a sample density thing. So if you were to compute a sample density, so kind of like a ratio of how many samples there are for an area, for a uniform distribution, you would think about it this way: to generate an obscenely large amount of samples, divide the domain into grids, and then compute the ratio of how many samples are in that particular grid cell out of the total, and then divide that by the area of the square.
Mm-hmm.
And for a uniform distribution, this should be a uniform number. Every single grid should have the same number of samples. If your samples are drawn according to a uniform distribution, it doesn't matter if they're actually random or if they're a low discrepancy sequence or anything like that. If they're supposed to be uniform random distribution or follow a uniform distribution, then their density will be constant. It doesn't matter what way you choose to pick the samples, it just needs to be progressive. Allow you to basically augment the count into infinity. And now that does the stretching, the transformation of the samples coordinates from one space to another is a continuous function, and it's also I wouldn't say monotonic because that's not the right word, but it's a it's a continuous bijection. So every single sample in the outgoing distribution has an inverse. So for every single sample, I can kind of map it back to where it came from. So for every single input, there's only one possible output, and for every single output, there's only one possible input. So it's a bijection. Because it's a bijection, that kind of ensures that the samples which are within one square, after you transform them into their new positions, they're going to be within the same patch. Well, not necessarily a square, but they're going to be within the same patch, continuous patch. Obviously, there are certain transformations which have discontinuities, such as sampling the visible normal distribution of a GGX distribution or any sort of other distribution, where, for example, you've got the sphere, and then you kind of the ellipsoid, and you partition it into two different parts for two different projections. The one which is planar, and the one which is orthogonal to the light view or to the observer. So that's where the discontinuity gets introduced. But aside from that, those functions are generally very continuous. They will have a limited discrete number of discontinuities. And because of that continuity, in the general case, this patch will be transformed into another patch. And then because of the bijection and everything like that, the samples will stay within that patch. So that means that if you were to estimate the density of these samples, right, the number of samples doesn't change, only the area of the patch changes. And the Jacobian tells you how much the area changes.
Yeah, I got it.
And now, this doesn't matter if you are in 2D or if you're in 3D, because then you're talking about differential volumes. But basically, what you should notice is that there's no other way for this to make sense except that the area must change. So the density of the samples is proportional to the probability density function that you're supposed to be sampling, like with regards to, right? So if the area shrinks and there's the same number of samples inside, that means that the density of the samples increases.
Yeah, yeah, right.
And the density of the samples should be proportional to the probability density function. So that's why we have this relationship that 1 over the absolute value of your Jacobian should be equal to your probability density function. For transformation, for sampling transform from the uniform distribution to a distribution that you think you are sampling with regards to your algorithm. So, and this actually can be extended a lot further because this is basically equivalent of saying that Jacobian times the probability density function is 1, right? And you can kind of extend that one step further and think about what would happen if you were transforming some other probability density function. Like, for example, you had the ability to generate samples with another distribution, like let's say triangle distribution or the normal distribution with a Box-Mueller transform or something like that. So you had something else than a normal distribution. Sorry, not normal, the uniform distribution. And you wanted to plug that into a transform or transforms from that distribution to another distributions. And if you wanted to check whether that transform works, you'd have to just compute the Jacobian of that transformation from one probability distribution to another, multiply it by both probability distribution functions, and then that should be 1 at every single point. And then you could do an arbitrary amount of transformations from one probability distribution function to another of your sample distributions, and all that would be is just the probability of the first one, the one with where you source your random variables from, the probability of the last one, and then the Jacobian, the determinants of the Jacobians all multiplied together. For the past 5 minutes, I've been using Jacobian as a shorthand for the determinant of Jacobian, but we mean the areas of the determinant of Jacobian. Yeah. So this basically should all work, and the way to actually do this test numerically in practice is to use finite differences. So you have your sample, and then with the sample, we add some offsets, and then from these finite differences of where that sample gets transformed to, we get an approximation of the Jacobian. And this is very easy to do in pixel shader because you got that df/dx functions. So you can do this test in 2 dimensions on a uniform grid with a pixel shader, no problem. Where you use the pixel positions as the random numbers, the uniformly distributed samples. If you get what I mean. So basically, this should all work. This should all work because what you should be able to do is basically. So what you should be able to do is basically do a basically take a sample, add a small offset, find out where that sample and the offsetted sample did transform to, divide that by the original distance between them, and you've got yourself a directional derivative. Yeah. And out of, however many, for rendering, we're mostly talking about 2D to 2D transforms. So a point on a square to a point on a hemisphere. But you generally want to essentially take two directional derivatives that will give you the Jacobian, and the directions obviously need to be orthogonal. So you can do it in a pixel shader with dfdx, but you can also do a stochastic test where you actually pick that sample position randomly or from a low discrepancy sequence. Obviously, you have these offsets preset prefixed, so they'll always be the same. And for every single one of these samples, you basically do two directional derivatives to compute the determinant of the Jacobian. And the cool thing about this approach is that, technically speaking, it would allow you to test multiple roughnesses, because the first two dimensions of the random number you could take to be the random samples which actually get put into the importance sampling function, to determine a light direction to sample. But then you could take additional dimensions of the random sequence or the low discrepancy sequence to become, a roughness variable or a different view direction, a different observer direction, different index of refraction, and then you'd actually be able to test all the essentially the entire domain of your BRDF or of your sampling function for all the different parameters. So yeah, so I mean that about wraps it up. And really important thing is that finite differences, the smaller the difference is, the smaller this difference is going to be, and also the smaller the denominator is going to be, the difference to get the finite difference. So that means that you're going to have a small number, floating point number, divided by a small floating point number, which is going to yield a big floating point number, which is then going to be multiplied with probably a small floating point number, basically to come out as one. So it's kind of very important not to do the test in a way like this. So you've got your absolute value of the Jacobian determinant, and then you're doing a difference with the reciprocal of the probability density function. You don't want to do a test like this, because of the way that this will work for really huge kind of probability density functions. That for example, for a delta distribution, or for well, actually for delta distribution this doesn't matter, but for really narrow distributions, like a really narrow box functions, or a Gaussian with a really small variance, this is going to be a very small number. Yeah. And this is going to be a number that has been produced by taking a difference of of a very small number divided by also a small number, right? And then because they're going to be small, that's going to lead to a lot of inaccuracy. And then that especially with stuff like DFDX, that doesn't have a lot of floating point bit precision, not as much as you hope and want. So this can really easily, like if you're going to display this visually as an image between 0 and 1, that can very easily mislead you, because if for example, if this thing has a low probability of occurring, right? So the probability is like very tiny, like the tail of the Gaussian, right? And then this will also have to be very big to compensate for it. by the time this number gets to be, six digits long, then by subtracting them, the floating point standard will give you quite big errors, like maybe one even. And even if it's not one, even if these numbers are only 4 digits long, like a few thousand, then the error from subtracting them can be actually quite perceivable. Like a small shade of gray or something like that. So what you're not interested in is the absolute error. You're not interested in the absolute error. You're interested in the relative error. And that's why a test of this form is much better. Because how much that will deviate from one will basically indicate the percentage error between them.
Mm-hmm.
Yeah. And that's why, for example, in our unit test, I had to change it from this into that because I was falsely throwing up positives.
Okay.
Okay, I think that about wraps it up.
Mm-hmm. Okay.